Good day, everyone. Welcome to our lecture. Today, we will be discussing about some topics in probability, especially on independence, conditional probability, product rule, and Bayes rule. For this video, we will be discussing the first three topics, and that should start from conditional probability to independence and multiplicative rules. Let's start with conditional probability. No, the conditional, when we say conditional probability, it's getting the probability of an event provided that another event had occurred. Say, for example, we have an event A and an event B. In order for us to determine the probability of event B using conditional probability, it should be that event A had occurred. Say, for example, this one, if we want to find the probability that an individual has the disease given that the diagnostic test is positive. So here, if we'll assume that this one, an individual has a disease, this will be our, say, event B, and the diagnostic test is positive, so this will be our event A. So we can find the probability of event B given event A. So provided that event A had already occurred. This is how we denote conditional probability and is read as the probability of B given A, or the probability that B occurs given that A occurs. And okay, and we denote again using this notation. So we can find the conditional probability, the probability of B given A using this one, the probability of the intersection of events A and B divided by the probability of A, provided that the probability of A is greater than 0. Otherwise, this would result to an indefinite value. Now let's have this example to understand better um, conditional probability. So let's try to solve some examples. Suppose that the sample space is the population of adults in a small town who have completed the requirements for a college degree. The data are categorized according to gender and employment status. So here in table 2.1, so this is now the equivalent data. And one of these individuals is to be selected at random for a tour throughout the country to publicize the advantage of establishing new industries in the town. We shall be concerned with the following events. A man is chosen and the one chosen is employed. If we check it in our table, we have here the columns are the employment status. We have employed and unemployed, and in the rows are the gender. So there are 460 males that are employed and 40 which are unemployed, 140 females that are employed, and 260 that are unemployed. Now, if you are given only this portion here, it would be better to get the total for each column and each row. So for the rows, the total is there are 500 males and there are 400 females. For the columns, you have 600 are employed and 300 are employed. Now, if we want to find the probability of a man is chosen given that he is employed. So how do we find the probability this probability? Remember that the probability given the previous definition, the probability of B given A is equal to the probability of the intersection of events A and B divided by the probability of A. In this case, since we use the variables uppercase M and uppercase E, then we'll change our equation to the probability of M intersection with E divided by the probability of E. So which means we'll get the probability that a person or a man is employed. Okay, a man is employed divided by the probability of all the employed people. And how do we solve it? Okay, so again, we find the probability that that man is employed divided by the probability of all the employed. Okay, employed people. Now, let's get the probability here by using the table. As you can see, this will be an employed man, right? So that's 460. But this is not the probability of the intersection of E and M, but the number of sample points of the intersection of E and M. So how do we get the probability of that? So we will divide this by 900. Why 900? Because this is the total number of the people who were um, in this data. Okay, so we will then have 460 divided by 900, then get the total probability of those employed. No, we have, of course, these are the employed people. You have 600. Okay, it includes male and female. So that is why you have here 460 divided by 19 all over 600 divided by 900 rather. So we will cancel out 900. Then we will simplify this and we'll get 23 over 30 and approximating the value. So this is written in this way. So approximately this one. Okay, that's 0.7667. So this is now the probability that the person selected is a man, provided that he is employed. Okay, so that's the answer. How about the other way around? What if we are asked, find the probability of the one chosen is employed given that he is a man. That person chosen is a man. In our previous example, we are asked to determine an employed male or a man, given that he is employed. Here, find the probability of an employed person, no, chosen, given that he is a man. So what is the difference between the two? So this is how we solve this one. If you recall, okay, so let's go here. If you recall, our formula is the one at the right side should be at the denominator. In our previous example, we have P, finding the probability of M given E, which means that our denominator is the probability of E. Here in this case, our denominator will be the probability of M. So that's the difference. Now, we'll have to check the one on the right side. Then, taking a look at, of course, the intersections of the two will be just equal. A man that is employed and an employed man, okay, is just the same. So we will use 400 and divide it by 900 to get the probability of this. Okay, this is 400 over 460 rather over 900 divided by the probability of all males, okay, of all man. Okay, because in the given condition it says that given that he that the person is a man, so the total number of males is 500 divided by 900. In the same process, cancel 900 out, simplify the remaining values, and you'll get 23 over 25 or exactly equal to 0.92. So this is how conditional probability works. Remember, again, that the denominator will be this one, the one on the right side. So this is again read as the probability that that the person chosen is employed given that he is a man. Okay, let's take these examples. We have here another problem. The probability that a regularly scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.82. And the probability that it departs and arrives on time is 0.78. Now, in this case, we're actually given with these values. They are already in their probability forms. Okay, let's denote that when it departs on time, that will be the probability of D. Okay, let's denote that the plane or the flight departs on time is D. Then the the flight arrives on time is event A for arrive. So that probability of D is 0.83 and the probability of A is 0.82. And this one here, it is said that the probability that the flight or departs and arrives, or the plane departs and arrives on time. So since this uses the word and, so this is the intersection of the two. So the plane arrives or departs and arrives on time. Again, we can interchange this by the rule of uh, Boolean algebra. So that's we can, or even the sets, using commutative law. So we can just say that these two are equal. So this is equivalent to 0.78. Okay, so we now have the given values. Okay, PD is 0.83. So the probability that the plane departs on time is 0.83. And the probability that the plane arrives on time is 0.82. And the probability that it both departs and arrives on time is 0.78. Now, we are asked to find the probability that the plane arrives on time given that it departed on time. And also, the probability that it departed on time given that it has arrived on time. You take note of the given conditions. So that is why it's called conditional, okay? So let's now proceed to the solution. So again, the probability that it departs on time is 0.83. The probability that it arrives on time is 0.82. And the probability that it departs and arrives on time is 0.78. So going back to our equation or our definition, that the probability of B given an A event is equal to the probability of their intersection divided by the probability of the condition. That's the probability of A. So for this case, we use, okay, it arrives on time given that it departed on time. So our condition here is D. Okay, and we have to find the probability of A. So replacing all of this, our equation will become the probability of A given D, and that is the probability of the intersection of D and A divided by the probability of D. Then we will substitute the values, okay, in the right side, and that would be 0.78 and divided by 0.83, which is equal to 0, approximately equal to 0.9398. So this will be our final answer. Okay, we can conclude that the probability that the plane arrives on time given that it departed on time is 0.9398. Now let's proceed to the second question. Okay, it's now a different situation here because our condition is now it has arrived on time, and we are solving for the probability that it departs on time, okay, based on our given condition. So same given values, and now take note that our denominator has changed because this is now the condition. And substituting the values of these values here now in the right side of the equation, that will be 0.78 divided by 0.82, or is approximately equal to 0.952. So the probability that the plane departed on time, given that it has arrived on time, is 0.9512. Okay, now let's have another example. Now for this case, you will be going to solve or show the solution. I get your pen and paper and solve this one. I have already shown the answers to the problems. So your task will be to show the solution. Now there is an article which is entitled "Chances Are You Know Someone with a Tattoo and Is Not a Sailor," which is included results from a survey of adults aged 18 to 50. The accompanying data are consistent with summary values given in the article, which is shown here. And if an individual is selected at random, find the probabilities that the person selected or individual selected has a tattoo. B, the person has tattoo given that it's his or her age is 18 to 29. C, the person has tattoo of age 30 to 50. And D, a person is in age 18 to 29 given that he has a tattoo. Again, as I've told you earlier, you have to determine the total of each for the columns. Okay, the total for the columns, get the total, and also the total for each rows. So you put total here and total for the columns. Okay, so I hope you can get the answers right. Okay, our next topic will be independence. Okay, when we say independence, it is defined in this manner. Two or more events are said to be independent if and only if the probability of event B is not affected or influenced by the change or occurrence of event A and vice versa. Otherwise, if the event A is affected by the occurrence of the other event, which say event B, they are dependent events. Again, we can say that events are independent if the occurrence of the two does not affect each other. Two or more events does not or do not affect themselves. However, if one or two events affect another, then they are dependent events. We have here another definition. We can say that independence are events are independent if and only if the probability of B given A is just equal to the probability of B, or the probability of A given B is just equal to the probability of A. Okay, assuming that the existences of the conditional probabilities. Otherwise, they are dependent. Okay, let's just try to identify whether the given, so we will not solve this one, but we will just identify whether the given statement or the events in the given statement are dependent or independent. Let's start with the first one. Suppose a researcher notes a person's gender and whether or not the person is colorblind to red and green. Thus, the probability that the person is colorblind change depending on whether the person is male or not. Okay, now, we have two events, person's gender, okay, and the other one is if he is colorblind to red or green. Now, actually, the answer here is that the probability that the person is colorblind is actually dependent on the gender. That is because, according to study, only male individuals are colorblind. okay, or have the probability or a possibility that to be colorblind. Females are not colorblind. In fact, females can identify colors more than males can. Next, an urn contains 4 green marbles and 6 red marbles. What is the probability of getting 2 red marbles? So the marble here is not replaced after being drawn. Meaning, if I have an urn, how do I create an urn? So let's just say this is an urn, and there contains 4 green marbles. Let's have 6 red marbles, and let's change the color to green, and 4 green marble. Okay, what is the probability of getting 2 red marbles? Now, are these dependent or independent events? No, these are actually dependent events. Why? That is because when we get one marble, change the color. When we get one marble, okay, the number of marbles inside the urn also gets lesser. Okay, so suppose we get one marble. So how many marbles were left? Would be 9 instead of 10. And also, so if we get a red one, its probability first, no, at the first draw, that's 6 over 10. However, since we already get one, when we get another one marble, suppose it's red again, however, its probability is now 5 over 9, which means the probability of the occurrence of the second event is affected by the occurrence of the first one. So these events are dependent events. However, if the statement says that after getting the marble, it would be replaced, no, after being drawn, meaning when I get the first marble, so I will place it back and get another one, then these can be independent events. Okay, you take note of the difference. Here, in this problem, since the marble is not replaced or placed back in the urn, so that means that the probability of the marbles inside the urn are affected by the first draw. Okay, so these are dependent events. Okay, so as I have said earlier, so this now when the marbles are replaced after drawing, so these are now independent events. Okay. Number 1 and number 2 is dependent. Number 3 is independent events. Next, a football team is involved in 2 overtime periods during a given game, so that there are 3 coin tosses. 3 coin tosses. If the coin is fair, meaning in the sides of the coin, one side is head, the other is tail. What is the probability that they lose all 3 tosses? Again, our purpose here is just to determine whether events are independent. We will do the solving later. Now, since the coin is fair and the coin will be 3 coins will be tossed, which means the occurrence of the first coin or the occurrence of the second coin will not be affected by the occurrence of the second one, because here we have a 1/2 probability. Also in the second toss, we also have another 1/2 probability, and in the third coin or toss, we have another 1/2 probability. As you can see, the probability of one coin is not affected by the other. So these are independent events. And how do we check for independence? If we go back to the definition, now the event, the probability of one event given another event is independent. The events are independent if this is just equal to the probability of E sub 2. No, the probability of E sub 2 given E sub 1 is equal to the probability of E sub 2. And we can get the probability, the intersection, okay? Since they are independent, the intersection of the events is just equal to the probability of the intersection of the events is just equal to the product of the probability of each events. Okay, let's have this example. Two coins, toss two coins and observe the outcome. Define these events. E sub 1 is head on the first coin, E sub 2 is tail on the second coin. Are these events independent? So using our definition or test there earlier, that the probability of the intersection of two events, say E sub 1 and E sub 2, these events are independent if the result is equal to the probability of E sub 1 multiplied by the probability of E sub 2. So what's the probability of E sub 1 first? Okay, the probability of E sub 1 is 1/2, right? And the probability of E sub 2, okay, uh, okay, we get a tail on the second coin. So it's also 1/2. Now, can we say that these events are independent? Before that, let's identify first the sample in our sample space, the outcomes, okay, in the events. So take note that we are tossing two coins, okay? So the possible outcomes would be the first will be head, the second coin will have head also, and we can also have head for the first, tail for the second, or tail in the first, head in the second, or tail on both coins. As you can see here in our event 1, head is on the first coin. So you have, okay, these two. So that's why we have 2 out of 4, or simply 1/2. Then we have tail on the second coin, these two here, right? And that's also 2 out of 4. Now, the we are looking or checking if these two are independent events. Now, if we combine the two, head on the first coin, tail on the second coin, which among these outcomes has head on the first coin and tail on the second coin? If we check the outcomes, that is in the second sample point. And this is actually our intersection of E sub 1 and E sub 2. Again, when we say intersection, this is the common outcome of events. So if this is our event 1, okay, and this is our event 2, then their intersection is this one, which is asked in this problem. And what's the probability of this? The probability of the intersection, since there is only one common outcome among the sample space, among the outcomes in the sample space. So that's 1 out of 4 outcomes. So we should have here 1 over 4. Then how about the other side? Again, we just have to multiply P, the probability of E sub 1, which is 1/2, and the probability of E sub 2, which is also 1/2. Okay, again, by the way, if you see this sign, double equal, this is actually comparing if two are equal. No, the two sides of the equation are equal. Okay, then 1/4. Then what's the product of 1/2 multiplied by 1/2? So that is 1 times 1. That's 1 divided by 2 times 2, which is 4. Now, since the left and the right side of the equations are equal, therefore, these two events are independent events. Okay, therefore, E1 and E2, E sub 2, are independent events. Independent. Okay, so I hope you have understood the discussion. Let's now discuss multiplicative rules. So in this topic, we will be discussing how to determine the intersection of events without listing the outcomes or the sample points in the sample space. Okay, and here, if we go back to the definition, okay, let's go back to the definition in the conditional probability. The conditional probability or the multiplicative rules, or we call it the product rule, is actually a derivation of the conditional probability. If you recall, you have finding the probability of B given A is equal to the probability of the intersection of A and B divided by the probability of A. Now, in multiplicative rules or product rules, we are looking for this one here. So therefore, we will cross multiply this so that what would be left on one side is the probability of the intersection of A and B, and on the other side would be the probability of A multiplied by the probability of B given A, and provided that A is, or probability of A is greater than 0. Okay, here in this case, okay, again, here in this case, the conditional probability is given, and we are looking for the probability of the intersection. Now let's have this example. Suppose that we have a fuse box containing 20 fuses, okay, a box which has 20 fuses, of which 5 are defective. Okay, take note that 5 are defective. If 2 fuses are selected at random and removed from the box in succession without replacing the first, what is the probability that both fuses are defective? So take note here that we have a conditional probability, no? Because in the second selection, the number of fuses will be subtracted or deducted by 1. Okay? Going back on our equation, so if we use a sub 1, no, when a sub 1 denotes that the fuse, no, the first fuse selected is defective, and a sub 2 would be the second fuse is also defective. And take note that we won't replace or put back the first fuse. So meaning these are independent events. No, again, these are dependent events because the outcomes or the probability of a sub 2 is affected by a sub 1. Then checking our definition, so this will be the probability of a sub 1 multiplied by the probability of a sub 2 given that a sub 1 occurs. if we take a look, now, if we identify what is the probability of A sub 1, so that will be our first selection. Since there are 20 fuses in the box and 5 of which are defective, so the probability of A sub 1 will be 5 over 20. Take note that A sub 1 is the first fuse selected is defective. So that's equal to 1 over 4, right? Then, how about the second one? Okay, now take note that event A sub 2 is the second fuse selected is also defective. Now, as you can see here, there are already, um, there will only be, since we get the one fuse, and say that that's defective, so what would happen? The number of fuses in the box will become 19. So since we deduct 1, and since we got 1 defective, so the number of defective left would be 4, and that is 4 over 19. Now the question here is this the probability of A sub 2? No. That is because each of which, no, P sub, the probability of A sub 1 and the probability of A sub 2 are all 1 over 4. However, in this case, since we did not replace the fuse when we got in the first one, this will become the probability of A sub 2 given that A sub 1 had occurred, given that we already got one fuse. So that is why this 4 over 19 is actually the probability of A sub 2 given A sub 1. So this is now our conditional probability. Then if we check our equation, you have probability of A sub 1, then probability of A sub 2 given A sub 1. So we will substitute the values here. So that's 5 over 20, or simply 1/4, multiplied by the conditional probability, which is 4 over 19, or 1 over 19. Now, since this is equivalent to 1/4, then we can cancel out again 4 here. So there is the remaining, or the simplified form, would be 1 over 19, or approximately equal to 0.0526, which means if we convert it into percentage, we only have 5.26% probability that both fuses are defective. Okay. Oh, sorry about that. Okay, now we have another problem here. So the solution is already shown. Anyways, I will be just explaining this, how this problem was solved. So one bag contains 4 white balls and 3 black balls. Okay, this is in the first bag. The second bag contains 3 white balls and 5 black balls. So that's um the second bag. One ball is drawn from the first bag and placed unseen in the second bag. So if you have a first bag, so how do we create a bag? Okay, let's just say that this is a bag, an old bag, and this is the rope here. Okay, okay, we will get one ball and transfer it to the second. Okay, now our first event will be getting the ball here, right, from the first bag. Then the second event would be getting the ball here in the second bag. However, in the second bag, there is already another ball that is added from the first bag. Okay, initially, our first bag has 4 white and 3 balls. Now, what would happen to the second bag? So what if you will get a black? Getting a black black ball here in the first bag has the probability of 3/7 since we have 7 balls, right? Then what would happen to bag 2? Bag 2 will now have 6 black balls and 3 white balls. That is if the ball that we got from the first bag is black. Now what if it's second? What if we got a white ball? So the probability of white is 4/7. And what will happen to second bag? It will now have 4 white balls and 5 black balls. Okay. Now, again, one ball is drawn from the first bag and placed unseen in the second bag. The question here is what is the probability that a ball now drawn from the second bag is black? Okay, we are actually looking for the probability that the ball drawn from the second bag is black. There are actually two possibilities, right? So here we can get black, right, from the from the second bag, no, provided that in the first bag we got black. So we got the black, and also we can also get a black ball here in the second bag if the first ball that we got from bag one is white, right? So there are two possibilities. That is why we get here. It's either uh, we have this, no, the probability of getting in the first bag is black, the second is black, or we can have in the first bag is white and the second bag is black, both. Now, these are now the probabilities. Okay, this is using tree diagram. So since we already have 9 balls in the second bag because we got one from the first bag, however, it depends on which color did we get, no, from the first bag. So if it's black, so the probability will become 6/9. Okay. We won't consider this since that's white. No, we get white. So we are only considering, or we are only concerned with getting a black ball on the second bag. Then here we also have another. Um, this is actually not 6/9. No, this is 5/9. So please correct me. This is 5/9. Okay, since we have 5 blacks here out of 9 balls. Okay, so since we are um, considering this, now that would be, we will multiply this to get the intersections. Okay, or simply the probability. Okay, the probability of getting black provided that it's we get black from the first bag. So that will be this one. That's 3/9 or 3/7. Sorry, times 6/9. And also this one, we will consider this since we are on the other one. Okay. So we will also consider this since we will get black from the second, however, we get white from the first. So it's written here. So that's 4/7 times 5/9. Okay. So this will be, so if we rewrite this, if we write the detailed solution here, this one is actually the probability of B sub 1 times the probability of B sub 2 getting black on the second bag, given that we get we got a black bag on the first bag. Here we can rewrite this as the probability of getting white in the first bag times the probability of getting black in the second bag, provided that we got white from the first bag. So that's this one, no? This is also this one. Then we'll just add these two. So that's 3/7 times 6/9 plus 4/7 times 5/9. And simplifying, that's 38/63 or 0.6032. So that is how we use multiplicative rows. I have shown you two possible ways, no, in using the multiplicative rows or in following the multiplicative rows. Here in the second example, I have shown you how to use the tree diagram. Now you can use a tree diagram based on or depending on the problem. So see, we used here a tree diagram because it would be difficult for us to think or to imagine how do we solve this problem. Okay, if you think you cannot solve the problem using just following the previous equations, then we can use a tree diagram to say illustrate better our solution so that we can analyze the problem better. Okay, so that's um, multiplicative rows. Now we also have another definition here, which is actually provided in the checking of the independency of events. Now, if you go back to our previous lecture, we can check events if they are independent, now given this one. Now, since we already proved that the probability of the intersection of A and B is exactly equal to the probability of the product of the probabilities of events A and B. So we'll now have here a definition. Now, therefore, to obtain the probability of two events or that two independent events will both occur, simply find the product of their individual probabilities. Just like in this example. A small town has one fire engine, one ambulance available for emergencies. The probability of the fire engine is the probability that the fire engine is available when needed is 0.98. Okay, so our first event would be the fire engine is available when needed. And the probability that the ambulance is available when called is 0.92. So our second event is that the ambulance is available when called, and its probability is 0.92. In the event of an injury resulting from burning building, find the probability that both the ambulance and fire engine will be available. Now, the first thing that we have to do here is to check if these two are dependent or independent events. If we analyze the problem, fire engines, okay, the firemen are actually independent from the ambulance. Okay, since the ambulance are in the rescue side, okay, or in the hospitals, well, fire engines will be on the firemen or in the fire department. Okay, so these two are independent events. And how do we solve this? Okay, so recall our definition earlier that we have here the product of or the probability of the intersection of two independent events is just equal to the product of their probabilities. So if this is again our event A, so the probability of event A be equal to 0.98. And if our event B is the ambulance is available, and its probability based on the problem is 0.92. So to get the probability, both fire engine and ambulance are available, then we'll just have to multiply these two and we'll get 0.906. So the probability that both are available is 0.9016. Okay. Now we have an extension, a definition which is an extension of the previous definitions. In this definition, there are more than two events involved. No, that's a sub 1, a sub 2 until a sub k. So if there are four, so this will be a sub 1, a sub 2, a sub 3 until a sub 4. If events are dependent, so we will use this notation. So we have the probability of the first event multiplied by the probability of the second event, given that the first event had occurred, multiplied by the probability of the third event, given that the first and the second event had occurred, and so on. However, if they are independent, rather, we just have to multiply their probabilities. Okay, so that's the extension of the definition. And okay, this is the example for our previous definition. So there are three cards drawn in succession without replacement. So you take note of, please take note of what were written in the sentence. Now take note of the statements. Okay, the cards were not replaced. Okay, from an ordinary deck of playing cards. You take note that in an ordinary deck of playing cards, there are 52 different cards. Then we have to find the probability that the events a sub 1, a sub 2, a sub 3 occurs. Okay, we'll get the probability of the intersection of these three events. And what are these events? A sub 1 is the event that the first card is a red ace. A sub 2 is the event that the second card is 10 or jack. And A sub 3 is the event that the card is greater than 3 but less than 7. Now let's identify first the elements or the sample outcomes of these. The first event, okay, the first event here is A sub 1 and the first card is an ace, right? Okay, how many aces do we have in the deck of playing cards? There are actually four aces, and we have diamonds, heart, spade, and clubs. Now, two of which, the heart and the diamond, are color red. So therefore, there are two red aces in the deck of playing card. Next is we have the second event, which is the card is 10 or jack. Just like the aces, we have four tens and four jacks. So adding them, we have 8 jacks and 10. Okay, in the set of the deck of playing in the deck of ordinary deck of playing cards. The event 3 is that the number is greater than 3 but less than 7. What are numbers greater than 3 but less than 7? These are 4, 5, and 6. And same with the other previews, we have 4 fours, 4 fives, and 4 6 in the deck of playing cards, and a total of 12. Okay, now we might say that these are the probability of the threes. But however, you have to take note that we are not replacing the cards, which means if we take out one, the number of the cards will be deducted with 1. So that will become a conditional probability. Okay, these are now the outcomes. In the first draw, we have 2 out of 52. And in the second draw, since we got 1, so the total number of playing cards is now 51. And in the third one, the total of playing cards is now 50. So that's what happened here. Okay, so these are now our values. And recalling our definition that the probability of the intersection of the three will be the product of the first draw of first, yeah, the product of the second, given that the first draw occurred, then the probability of the third one, given that the second and the first had occurred. So we just have to multiply them. That's 2 over 52, 8 over 51, 12 over 50. And simplifying, that's 8 over 5525, 5,525, which is approximately equal to 0.14, which means that getting a red ace in the first draw, getting a 10 or jack in the second draw, and getting 5, 6, or 4 in the second draw has just 0.014 or 0.14% probability. So that is how we use the previous definition. Okay, now I have here an exercise based on the previous discussion. So I hope you have understood. Otherwise, kindly play it back or go back to the previous slides. Now, if you want to, if you are still a little bit confused on the discussion, okay, then if you are now ready, you can answer this exercise. The probability that a doctor correctly diagnoses a particular illness is 0.7. Now, given that the doctor makes an incorrect diagnosis, the probability that the patient files a lawsuit is 0.9. What is the probability that a doctor makes an incorrect diagnosis and the patient files a suit? The answer here is 0.27. Why do you think it is 0.27? So you get your pen and paper and um, find or solve this problem. Like, show your solution. So check if you get 0.27 as the answer. All right, that's the first three topics, and I hope you have learned from them. See you on the next one, and in the next discussion, we will talk about Bayes rule. Bayes rule also includes um, total probability. Okay. Thank you and goodbye.